Hey, Precalc, this is going to be limits day 3. And to get started on limits day 3, you're going to see a graph that was pretty similar to what you had at the end of limits day 2, where it's kind of a crazy looking piecewise function here, and there's a bunch of limit questions that follow below this. So go ahead and take a look at this graph, see if you can answer the limit questions that follow below it. I'll show you some answers in really just a moment here. But if you want to give it a shot, see where you're at with the concept of evaluating limits based on a graph, I'd encourage you to do that. And here are the answers. So for numbers 1 through 4, all dealing with the x value -2. The limit as x goes to -2. Remember, that means from the left side of the graph. So you're starting over here and you're kind of scanning right. Would be 5. The limit as x goes to -2 from the right side. Start on the right, scan left, is going to be 2 in this example. Right, here's x equals -2 right here. And I won't go over the others in this much depth, but I really think -2 is one of the more interesting values because when I approach from the left, we're getting close to 5. When I approach from the right, I'm getting close to 2. But notice how f of -2 is actually not any of those values. It's where that closed circle is at 4. And that's what the answer says in number 4. Now, if the left and right hand limits don't match, we know that the limit as x approaches -2 in general does not exist. So watch out for cases like that. You can see if you move on to approaching 0 from the left and right, that the y value actually there is also 0. Therefore, the limit as x goes to 0 is 0, and f of 0 is 0. And what we'll see is, by definition, that makes the graph continuous at an x value of 0. Moving on to approaching 3 from the left and right. From the left, it's 3. From the right, it's 1. Therefore, the limit as x goes to 3 does not exist. And you can see the value for f of 3. You had to find the limit as x approached 4. Hopefully, you're okay when you got to x approaching 6. From the left, it's headed down forever, so it's going towards -infinity. From the right, it was heading up towards +infinity. So the limit as x goes to 6 does not exist. F of 6 has no value. You wouldn't really say does not exist for that. You would just say empty set. And finally, the limit as x goes to infinity is 1. So as the graph goes to the right forever, we're approaching that horizontal asymptote. But notice how the limit as x goes to -infinity, there's not really any asymptote drawn on the left side of the graph. The arrow indicates over here, excuse me, that as you go to the left forever, the graph's headed down forever, so that's why the limit as x goes to -infinity is in fact -infinity. If you have any questions about those, certainly let me know. But otherwise, if you turn to the back, we have some more algebraic practice that I want to take a look at. We've done some of these cases where to evaluate limits algebraically, all you're going to do is plug in the value that x is approaching and see what happens. And what we have to look out for is those cases where we get 0 over 0. So you might even want to just kind of check that out first. You plug in 2 to the top and bottom, you're going to wind up getting, in this case, 2 squared minus 2 minus 2. The bottom is 2 squared minus 4. So 2 squared is 4, minus 2 minus 2, well, that's a total of -4 there, so that's 0 on top. 0 on top does not mean that it's that indeterminate form yet. If you get 0 divided by some number that's not 0, then the limit is 0. 0 divided by a number is 0. Except in this case, the bottom's also 0. Okay, so when you get that 0 over 0, that indeterminate case, what you have to do is you have to simplify your expression if possible. And in this case, you can factor the top and the bottom. So we're going to see a lot of cases today where that might be the scenario, where if you factor the top and bottom, you will then be able to evaluate the limit. Top is factored into x minus 2 times x plus 1. Bottom would be x minus 2 times x plus 2. Okay, so if you factor that, you'll notice that the x minus 2's cancel, and those are the factors that were the issue, right? If you plug in 2 to those, that's where the 0 over 0 comes into play. But now if I take the limit as x goes to 2 of what's left over here, the top would be 2 plus 1. The bottom would be 2 plus 2. So the limit as x approaches 2 is 3/4 for this one. Okay, moving on to the limit as x approaches -1. You plug a -1 on the top, this is going to become a total of 2. Minus -1 is going to become a +1 there, so 3 minus 3 is 0 on top. The bottom is 0, so that 0 over 0 case again implies you're going to have to factor the top and bottom. and then evaluate the limit from there. We haven't factored anything with the lead coefficient in a little while, but luckily this is factorable. A good hint, by the way, is that you have to cancel that x plus 1 factor. So you probably want a factor that has x plus 1 in the numerator. If this is a limit that we can evaluate, you probably want to be able to cancel those factors like I was just saying. So what would be the other factor that pairs with that? It would have to be 2x minus 3. And you can double check, with some box multiplication there to make sure that that works out, which it does. The x plus 1s now cancel. So you can take the limit as x approaches -1 of the remaining quantity 2x minus 3. 2 times -1 minus 3 is -5. Okay, if you think you're pretty solid on some factoring techniques, you can try some of these others. I'll just kind of keep going and fill in the rest here, but if you want to hit pause and try some on your own, see where your factoring skills are at, go for it. But for number 3, hopefully you're going to see that plugging in 1 right away does give you 0 over 0. So we're going to have to factor the top and bottom. It's been a while since we factored x cubed minus 1, the difference of perfect cubes. So just be careful there. The pattern would be you get a binomial x minus 1, and then a trinomial that would say x squared plus x plus 1. Okay, so the cube pattern is kind of like take the cube root of each of these, that's the binomial, then square this first term, multiply x times 1 for the middle term of x, square that 1 to get the 1 down there. If you kind of forgot about difference of perfect cubes, look back to the very first unit on the website. You'll see plenty of examples of factoring with perfect cubes. Bottom's going to be a little bit easier for us because difference of perfect squares typically is a good factoring technique that we're confident with. Cancel those x minus 1s. So we're taking the limit as x approaches 1 of x squared plus x plus 1 on top, and then just x plus 1 on the bottom. So if I plug in 1 on the top, you get 1 plus 1 plus 1, which is 3. Bottom is 1 plus 1, which is 2. Final answer for that one is 3/2. Luckily, you won't have to hear me do number 4 because it's a typo. It's the same thing as number 1 at the top. Copy paste error on my part. Works out for you guys. All right, last one. I'm hoping you're looking at number 5 and it's kind of jumping out to you right away to say that when you have 4 terms on the top and bottom, that this is going to be a case of factoring by grouping. You should probably try and check that you're going to get 0 over 0 by plugging in that 2. And I believe that will be the case in this one. But if I do some factoring by grouping, the top would become, if you take out an x squared from the first group, you get x minus 2 left over. Take out a positive 4 from the second group, you get x minus 2. So the complete factorization on top would be the limit as x approaches 2 of, that's going to be x minus 2 times the quantity x squared plus 4. So hopefully you kind of remember some other good factoring techniques here. Bottom, if you kind of try and do the same thing, take out an x cubed from the first group, you get x minus 2. Plus the other group, there is no GCF, but it already is x minus 2. So if you take out x minus 2 in the denominator, you're left with x cubed. Just be careful. This group, there's really a 1 in front of it, right? So you would get x cubed plus 1 left over. And then from there, the x minus 2's cancel. I realize that this is still factorable, by the way, x cubed plus 1. But I'll tell you, you don't have to factor this any further to get the final answer in this case. So the x minus 2 factors, this was the issue as to why we were getting 0 over 0. And like I said, even though x cubed plus 1, you can break that down a little bit further. At this point, you really can just plug in 2 on the top and bottom. 2 squared plus 4 over 2 cubed plus 1. Top is going to be 8. Bottom's going to be 9. Right? So just a little bit more algebra. When you do those cases where you get 0 over 0, there are other techniques that might come up other than, let's say, just that difference of perfect squares like we saw on day 1. All right, we are going to do one more thing today. And the last thing we're going to do is a little bit more with limits algebraically, but it's not on that worksheet. So if you want to take a second, hit pause and grab some paper. We're going to do a limit evaluating that looks something like this. The limit as x approaches 4 of x minus 4 over the square root of x with a minus 2 after it. Okay, first thing I'm going to do is plug in 4 top and bottom, see what happens. Top, 4 minus 4. Bottom, square root of 4 with minus 2 after it. Well, maybe you're not so surprised here that 4 minus 4 is 0, and the square root of 4, which is 2, minus 2 is 0. So we get this indeterminate form. However, this is not one of those cases like we saw in the last examples, where I can just easily factor the top and bottom, and then from there be able to cancel and plug in that 4. So what you're going to do in cases where you have these radical quantities is we're going to multiply by something called the conjugate. Now, we've talked about conjugates in probably a few different regards in pre-calc this year, and you certainly learned them as early as Algebra 2. We're going to multiply by the conjugate of what's in that radical expression. So I'm going to go back to the x minus 4 over radical x minus 2 and try and just simplify this expression. The way I'm going to simplify it is I'm going to multiply the top and bottom by the quantity radical x plus 2. So the conjugate is this same binomial with a change in sign in between. If this said radical x plus 2 down there, it would have made the conjugate radical x minus 2 then. Okay, so hopefully that concept sounds familiar. Here's what I'll tell you. When you're doing this process, the top, which in this case is the non-conjugate pair product, right? These are not conjugates on the top. Don't multiply those together. Leave those as the product of those two binomials. Okay, it's going to save you a lot of steps in the end if you don't multiply those. When you do the bottoms, though, whether you're a box method or if you're a foiler, which it's much easier if you're a foiler, because I'm going to say don't do the outside inside of the FOIL, if you know what that means. Basically, if you do the box or FOIL, you're going to get two terms to cancel when you multiply the conjugates. So essentially what I can do is I can just do the first terms multiplied and then the last terms multiplied. And when I do that, that's going to be the resulting product there. If you don't believe me, do it off to the side. You're going to get x minus 4, because radical x times radical x is x. Negative 2 times positive 2 is negative 4. I hope that you can see now that we get that product in the bottom, why I don't want to multiply the top out. Because at that stage, it would be really tough to see that those x minus 4s on top and bottom actually cancel. So don't multiply the non-conjugate pair ever for these examples. Just multiply the conjugates. Okay, so when those x minus 4s cancel, I'm going to bring back that limit statement because that's actually pretty important. The limit as x goes to 4 of the square root of x plus 2. That's all that's left over on the top. So now at this point, I should have no issue plugging in 4 for x. The square root of 4 plus 2. So 2 plus 2 is final answer 4 there. And I think we'll need a little bit more practice with that concept before we feel confident with it. So let's just do a few more, and then the homework will just be some practice with some algebraic limits here. All right, so number 2. We're going to take the limit as x approaches negative 1 of the square root of 2 plus x minus 1 over x plus 1. If you plug in negative 1 just really quick in your head, you're going to get 0 over 0. Okay, you're going to get radical 1 minus 1, which is 0. Same thing on the bottom. So what do I have to do to fix this? We have to multiply by that conjugate idea. The conjugate is a little bit different in this case because we're used to, I think, multiplying by the conjugate of what's in the denominator to kind of rationalize something. But what you'll see with limits is that you can multiply by a radical conjugate even if the term is in the numerator. Okay, the conjugate of radical 2 plus x minus 1 is radical 2 plus x plus 1. So you have to multiply by that same thing, top and bottom. Don't change any of signs inside the radical, just the sign that separates those two terms on top. So we're changing that to a plus. I'm going to rewrite the limit as x goes to negative 1 of the conjugate pairs on the top. So when I multiply radical 2 plus x times radical 2 plus x, that's just 2 plus x. And then negative 1 times positive 1 gives you a minus 1. Remember, the non-conjugate pair, just like we saw in the last step, don't multiply those out. Don't do box method. It's just going to make your life more confusing in the end. Because what I need to have happen is I need that x plus 1 to go away. That's what's making the 0 in the denominator right now, which I don't want. And notice how when I clean up the top, if I combine like terms, 2 plus the negative 1 right here is a positive 1. So the top is really x plus 1 over the quantity x plus 1, radical 2 plus x plus 1. Great, now that I have the x plus 1 in common, top, bottom, cancel those out. And finally, we're taking the limit as x approaches negative 1. Remember that if nothing's left in the numerator, you have to write a 1 up there. 1 over the square root of 2 plus x with the plus 1 after it. And now you can take the limit as x approaches negative 1 and get a value that's not 0 over 0 anymore. Okay, so if you plug in negative 1 for x, numerator is definitely 1. This is going to become 2 minus 1 under there, which is 1. The square root of 1 is still 1. 1 plus 1 in the denominator is 2. Final answer to number 2 after all that is 1/2. I'm going to encourage you to try this next one on your own. I'm going to kind of go right through it. So the limit as x approaches negative 3 of 2 minus the square root of 1 minus x over the quantity x plus 3. I'm going to give you a few quick hints about it. It is 0 over 0, so you might as well start by multiplying by the conjugate. But I'll tell you the only trick to this one is when you multiply the top and bottom by the conjugate, you're going to have to distribute a negative. And I hope you'll understand what I mean when you get to that point in the process. Okay, so for this one, I'm going to multiply the top and bottom by 2 plus the square root of 1 minus x on the top and on the bottom. Okay, on the top where we have that conjugate pair, I'm going to multiply those together. So this is going to become 2 times 2, which is 4. Then I'm going to have to write minus. This is just going to be 1 minus x when I multiply those, but it's the quantity 1 minus x. Why did I not have to write the quantity in this one up here a second ago? It's because that quantity came first. So subtracting 1 afterwards, it didn't matter if I had parentheses here. But if I'm subtracting a binomial, that's the result of this product right here, that negative belongs to both terms. So we will have to distribute that in just a second. Remember that on the bottom, I'm not going to multiply those together. I'm going to leave the non-conjugate just as the product of those two things. Hopefully I can cancel that x plus 3 if I've done this correctly. All right, if I distribute that negative in, I'm going to get 4 minus 1, which is 3, so that's good. And when I negate negative x, that's positive x. So distributing the negative leaves me with x plus 3 on top, which is perfect, because that's going to cancel with x plus 3 on the bottom. Cancel those out. And last step, limit as x goes to negative 3 of the quantity 1 over 2 plus the square root of 1 minus x. If you plug in negative 3 for x, 1 minus a negative 3 is going to be a positive 4 under the radical, which is good, because the square root of 4 is 2. So the final answer to this one is a total of 1/4. So that one, it looked pretty similar to what we did in number 2, but had maybe a little bit of a different feel, especially that step where I have to distribute the negative sign in. So just be cautious for things like that. I'm going to put one more up here. This will probably be one of the longer lessons for the week, so stick with me for one more, just because I know there's one on the homework like it. And this actually has a similar feel to what we'll be getting into later when we actually get into like one of the major topics in the study of calculus. This last one's going to say the limit as h goes to 0 of the square root of 3x plus h minus the square root of 3x over h. So I think the weird thing about this one is that it has 2 variables in it. And if we compare that to the other 3, they only had the variable x. This one has x's and h's. So just make sure that when you evaluate the limit, you plug in 0 for h only. You're not plugging it in for x. When you plug in 0 for h, you're going to get the top to be radical 3x minus radical 3x, also known as 0. The bottom is going to be 0 because that's what I'm plugging in for h. So when you get 0 over 0, we have to do something to fix it, which in this case is going to be multiplying by the conjugate. The conjugate of the top is 3x plus h plus radical 3x Just make sure you do that on the top and the bottom. This is probably one of the tougher concepts, I would say, with doing limits algebraically, but it is an important concept and it will come up in the study of calculus for sure. Okay, when I multiply the conjugates on the top, limit as h goes to 0 of radical 3x plus h times itself is just 3x plus h minus, I don't have to worry about distributing a negative here. This is just a monomial, right? 3x. So it's going to be minus 3x over, don't distribute that h in, leave it as h times radical 3x plus h plus radical 3x. Okay, the non-conjugates, leave them separate. Notice how on the top, 3x's cancel. So now the numerator is h over h times radical 3x plus h plus radical 3x. Go ahead and cancel those h's now, top, bottom. And it's the limit as h goes to 0 of 1 over radical 3x plus h plus radical 3x. Remember, the only thing that you're replacing with a 0 is the h. So this right here becomes 0. So what does that mean? This is going to become 1 over radical 3x plus another radical 3x. And radical 3x plus radical 3x is better known as 2 radical 3x's. The weird thing about this one is that you don't get a strictly numerical answer. You get an answer that's left in terms of x, and that's okay. All right, we'll see that happen a lot more in the last part of our limit applications. So if you have any questions about this one or any of the others that we've done today, definitely let me know. Otherwise, you're going to be doing a couple of homeworks that will have questions just like it.